In 2019, humanity photographed a black hole for the first time. You've seen the picture. An orange ring, slightly brighter on one side, with darkness in the middle. Here's the part most people miss. That ring is not the black hole. The ring is glowing gas, outside it, whipping around it close to the speed of light. The black hole is the dark patch in the center. And what's inside that dark patch, we have never seen. We never will. Not because our telescopes aren't good enough, because of physics itself. Start with something simpler. Throw a ball straight up, and it comes back down. Throw it harder, it goes higher. Throw it hard enough, about 11 kilometers per second, and it never comes back. That's escape velocity. On the sun, escape velocity is around 618 kilometers per second. Now take a star far heavier than the sun and crush it into a city-sized ball. The gravity at its surface becomes so extreme that escape velocity climbs past 300,000 kilometers per second. That number matters because that is the speed of light. And nothing in the universe travels faster. So light itself can't get out, not slowed down, not dimmed. It simply has no path that leads away. That's all a black hole is. Not a hole, not a tunnel, not a cosmic vacuum cleaner. Just an enormous amount of mass, packed so tightly that the exit speed exceeds the fastest speed there is. Every star is a standoff. Gravity pulls inward, trying to crush it. Nuclear fusion in the core pushes outward, trying to blow it apart. For most of a star's life, those two forces are almost perfectly matched. That balance is what a star is. But fusion needs fuel. Hydrogen becomes helium. Helium becomes carbon. Then oxygen, neon, silicon, each stage burning faster than the last. The final stage of a massive star's life, fusing silicon into iron, lasts about a day. And iron is where it stops. Fusing iron doesn't release energy, it absorbs it. So the outward push vanishes. In under a second, a core the size of the Earth collapses to something a few kilometers across. The outer layers fall inward, hit that wall, and rebound in a supernova bright enough to outshine an entire galaxy. For a star up to around 20 times the Sun's mass, what's left behind is a neutron star. Above that, nothing stops it. There's no known force strong enough to hold the collapse. The core keeps falling inward, and a black hole is what remains. Around every black hole, there's a boundary called the event horizon. It isn't a wall. It isn't made of anything. You couldn't touch it. It's a location, the last place from which light can still get away. For a black hole, the mass of our sun, that boundary sits about 3 kilometers out. For the one in that 2019 photograph, 6.5 billion times the sun's mass, the horizon is wider than our entire solar system. Here's what's genuinely strange. If you fell through the event horizon of a large black hole, you would feel nothing. No barrier, no flash, no alarm. Space around you would look ordinary. You would simply have crossed a line you can never recross. Every possible route, every direction you could point a ship, now leads further in. Not because something is pulling you, but because inward has become the only direction that exists. Going back would mean traveling backwards in time. Gravity gets weaker with distance. On Earth, that difference is far too small to notice. Your head is 1.5 meters further from the center than your feet, and you feel nothing. Now fall feet first toward a small black hole. Your feet are closer, so they are pulled harder, much harder. The difference between the force on your feet and the force on your head becomes greater than the strength holding your body together. You get stretched, lengthwise into a thin strand, while simultaneously being squeezed from the sides, because every part of you is falling toward the same central point. Physicists gave this a name that sounds like a joke, but is the actual technical term: spaghettification. And here's the twist. The bigger the black hole, the gentler this is. Around a small one, you'd be torn apart long before reaching the horizon. Around a supermassive one, you could cross the horizon completely intact and only be destroyed much later, deeper in. Now change perspective. You're not the one falling. You're watching from a safe distance as a probe drops toward the horizon. Gravity doesn't only bend space, it slows time. The stronger the gravity, the slower clocks run. And this isn't a theory waiting to be tested. Your phone's GPS corrects for it every second of every day. Near a black hole, the effect becomes extreme. You would watch that probe fall, and then appear to slow down. Its signal stretches to longer and longer wavelengths, sliding from visible light into infrared, then into radio. It dims, it reddens, it freezes. From where you're standing, it never quite crosses. It just fades until there's nothing left to detect. But from the probe's own point of view, nothing unusual happened at all. It fell straight in a finite time, and kept going. Both accounts are correct. That's relativity. So, what is actually inside? General relativity gives a clear answer. All the matter collapses to a single point of zero size and infinite density. A singularity. Curvature becomes infinite. The equations stop producing numbers. And in physics, when your theory returns infinity, that is almost never a discovery. It's a signal that the theory has been pushed past where it works. Because at that scale, quantum mechanics takes over, and quantum mechanics does not allow anything to be located at a point of exactly zero size. So we have two theories. Both are among the most precisely tested ideas in all of science. And at the center of a black hole, they flatly contradict each other. Resolving that contradiction would require a theory of quantum gravity. We don't have one. So the honest answer to what's inside a black hole is this: nobody knows, not yet. And that gap is one of the biggest open problems in physics. We can't see in, but we're getting remarkably good at reading the outside. The 2019 image came from the Event Horizon Telescope. Not one dish, but 8 radio observatories spread across the planet, from Hawaii to the South Pole, all recording the same object at the same instant. Combine them, and you get a telescope effectively the size of Earth. In 2022, the same team imaged Sagittarius A star, the supermassive black hole at the center of our own galaxy, 4 million times the Sun's mass, 26,000 light-years away. And we track stars orbiting it. Watching how they move tells us the mass of something we cannot see at all. That measurement won a Nobel Prize. A black hole isn't a thing sitting in space. It's a region where space and time behave in ways our intuition was never built to handle. We've photographed the edge. What lies past it is still, genuinely, unknown. If you want more of this, subscribe.